record button officially and say, not Happy Garbage Day, because it was a holiday yesterday, so Garbage Day is tomorrow, and I'm going to be all messed up this week as a consequence. Bladimir, would you like to come up to the front here? I will make sure that you are in the camera.
Yeah, I'm here.
Oh, yep. You're going to
Yes, that's great. Thank you,
move this
Lisa.
back a little bit. Okay, I will do the doorbell, and then you've got the coffee show.
Great. I'll move this anyway. Hi, people in Zoom. I hope you are doing well. Hi, people in the classroom. I hope you are doing well too. So, today we will be discussing Formative Assessment 5. We have 3 questions. I read your answers. Thank you so much for your time. Your answers were incredible. I enjoyed reading all of your comments and opinions, so thank you for that. Question 1, you will see that's related to software and some differences. Question 2 was pretty interesting, so I think that I would like to hear your opinions about that question and some of the reasoning for some answers, and I will be mentioning some interesting things that I found. And question 3, I think that most of us agree on what should be included to improve or to answer the research questions based on the study we have. So I prepared, well, we will be reading the questions on the website, but I prepared this set of slides, just 5, to have some kind of references about some common points that we can mention with respect to the 3 questions we have. Now, this is a slide just because I didn't know how to present the information. So that was weird. I was thinking, how can I include something like the Word file for Formative Assessment 4? But then I thought, that's just a Word file. Let's do a set of slides. I don't know why, but here you have a set of slides. Because why not? Exactly.
Can you remind us what the design is before we jump into the answers?
Yes, exactly. So let's go back to the story. So this is our story. Should I read it? Read it?
Yeah, you can hit the hyphens.
Sorry?
You can hit the hyphens.
Which ones?
Oh, sorry, just like summarize the story.
Oh, okay, great. Yes, I'm not good reading. I'm a grad student. So here we have our story. So basically, we have data about the weight loss training program, and a group of researchers are interested in trying to capture differences after completion of the program and how weight kept after that program, which is the follow-up event. Some details about the data they have is, first of all, they had 25 participants. They were collecting 3 measures of weight, because weight is the dependent variable. So first time point should be representing the baseline. Then we have the results after the 6-week program. And then we have one measure after 12 weeks. That's the follow-up session. Okay? So we have a baseline. We have the information after completing the program. And then we have the follow-up session. The second occasion, the difference between occasion 1 and 2 is 6 weeks, and the difference between occasion 2 and 3 is 12 weeks. Okay? They are expecting, there we go. They are expecting individual differences in change, both in the response to the training program and success of weight maintenance. And this is the different options they had for different software. So questions about the story? Is the story clear? Okay, we have 3 time points, we have weight, and we are interested in differences after completing the program and how that weight was maintained after 12 weeks. Okay? So question 1 is related to the different options they had to fit the model in Stata, SAS, or R. So here we go with question 1. What do you think is weird or wrong or could be done better in this code? Any ideas? Yes?
This is in particular to this data code. I think it should be using REML instead of maximum likelihood.
Yep.
But if they wanted to stay within maximum likelihood, they would need to put a different degrees of freedom method.
Yes. So let's start with data, right?
Yeah.
Yes. So in this case, we know that we are using these degrees of freedom with ML. But the first thing mentioned was instead of ML, what should we use or what they should use? REML. Why?
Because it's a smaller sample size.
Exactly. Because of the sample size at level 2, we just have 25 participants. Can that be considered enough for this model? I don't think so, right? Could be, but in these cases, it's advisable to use REML just because we know that maybe we don't have enough sample size at level 2. So yes, first thing, across software is using ML instead using REML instead of ML. And you can see in SAS, we should be changing this part. What I'm doing. That's what I have. The slide. So, in this case, we know that instead of ML, we should have REML across software. So here you have that part. Data is here, and R is here in the Elmer package. Okay, one thing. What's the other thing that you would mention? What else is wrong here? We have 1 and 3 are left, I think. Yes. What do you think about occasions here? Would you use occasion as in this way in this model? People shaking their heads. What do you think? Yes or no? Advisable or not? What's the reference for the fixed intercept with this variable in the model?
Can you repeat that question?
Yep, of course. What do you think about occasion in the model as is being used here?
And it's coded 1, 2, 3.
Exactly. Yes.
The coding
Here.
is wrong. We need to recode the data. So the first occasion needs to be time 0. And then, I don't know if this is true or not, but I think that the second occasion needs to be maybe time 6. And the third occasion needs to be time 18 because it's not an equal amount of time between occasions, but I could be wrong about that.
No, that's a good point actually. But that's related to other thing that I wanted to mention later. But let's divide your comment. So first, we know that right now occasion is coded with 1, 2, and 3, right? So with this variable in the model, the reference for the fixed intercept would be when the predictor is 0. That's always the case. The intercept is the predicted outcome when the predictors are 0. In this case, occasion 0. Does it mean something? Occasion 0 does exist? No, right? So maybe the interpretation of the fixed intercept would be wrong in this case, using this variable. Now, with respect to what's the meaning of 1 unit in occasion, that's another good thing that some people mention, because here, the difference between occasion 1 and 2, the 1 unit difference, the meaning of that is 6 weeks. That's related to 6-week period. However, the 1 unit difference between occasion 2 and 3, that's 12 weeks. So in this case, we have non-equal intervals. So the meaning of 1 unit difference is tricky in this case. And that's one of the things that we mentioned last class. I don't know if we should change time, the labels as, let's say, 0, 6, and 12. Because that's what occasion 1 means, for example. A period of 6 weeks, and occasion 3 means a difference of 12 weeks.
So 6 and 18 then, as you said.
What
So
could we do in that
0,
case?
6, and 18.
Oh, okay.
She said.
Or maybe we could do 1 and 3, but not have a 2. If you because I was thinking every week, but I suppose it doesn't. You decide what your interval is. So maybe 6 weeks is your unit. But then you would need to double it for the third measurement.
Yes, one of the options would be, instead of using 2 and 3, we could use 6 and 18 to represent weeks. But in that case, is that advisable?
I think it's fine. I think it's more intuitive to say per week than per 6 weeks.
Oh, yes.
As a unit, like a 6-week unit is a weird thing, unless you're talking like semester or whatever, because we agree that a semester is 17 weeks, and that's our unit of time.
Yes. Yes, so can we say that depends on the meaning of one unit means? Yes. The labels and the parameterization of the fixed effects. Okay. So we have mentioned 2 things. We have other 2 things related to code that we could improve here. Ideas, we already talked about occasion or occasions here and Dremel. There are other 2 things here. One of them is related to, no, but I think that you mentioned the third one. For Stata users, we cannot use the Satterwhite degrees of freedom when we use ML. We cannot. As simple as that, yes, we cannot. If you want to use Satterwhite, you should go, you should move from ML to Dremel. So that's the third one. Thank you.
Can we use Satterthwaite in R?
Yes. Oh, yeah, but you mean Satterwhite with ML in R?
Yeah.
That's a good question. Okay, yes, we can. And I think that's possible because for some models in Elmer, I've used ML instead of Dremel, and when I ask for the summary with the degrees of freedom equal to Satterwhite, I can see the results. But in that case, I don't know if Satterwhite is being applied just to the summary of the model results.
That's what I think is happening.
Which is slightly different, I think.
It probably varies by package.
Okay, so that's something that you can check by yourself. Good question. Can we use Satterwhite and ML in Elmer? I would say yes, but I'm not 100% sure yet. So, last thing is related to SAS and Stata. Yes.
Chat has one of them.
Yes.
No, in the chat. I'm saying.
Oh, yes. Thank you, Hilary. Yes. Covariance in Stata on the variance side is needed. Exactly. Specifically, we need to define the unstructured structure that we will have for what? The G matrix in this case. Why? Because we have 2 random effects right now. For example, here in R, we are saying that we have a random intercept and we have a random slope. In Stata is here, and SAS is here. So if we have 2 random effects, we know that the G matrix should be unstructured because we want the variances in the diagonal to be estimated plus the covariance, right? Now, something that's interesting that I didn't know is that the R matrix by default is set as independent, which is what we want to have for the residuals at level 1. Remember that right now we are assuming that the level 1 residuals or time-specific residuals will have just 1 variance and 0 for the covariances. And that's by default. I didn't know. So that was interesting. And here you have the answer key. So you can see in blue what things should be added to each of the software, and in red you have the thing that should be modified. I didn't include like the right options, but the things in red should be changed. Okay, so that's question 1. Additional questions? Is that clear? Great. So let's move to question 2 here. And this was interesting because I read, I think that maybe 3 type of questions, or so answers. answers related to what things could be different in terms of the procedure, what things could be different in terms of software and syntax, and things that could be different in terms of the study design. So, my question for you is, of course, do you think this model is the best way to answer the research questions? If not, what would you suggest they do differently?
I think they should account for nonlinear change. So they should account, like test if this could be like modeled by quadratic or stepwise models instead of that.
That's an interesting answer because Ahmed is mentioning that we should consider something non-linear. However, I read some answers that were suggesting, for example, a model with a quadratic time effect, which is linear. Well, yes, it's continuous instead of discontinuous. So, my question is, based on this part of the study, given that they are interested like in the differences between phases before and after completion of the program and after and keeping the program results, do you think that something continuous would be advisable? Why not? Why something continuous would be, let's say, inappropriate in this case? Why? Do you think that weight loss is... Sorry?
Is someone talking?
Yeah, I think it's outside, yes. So, why do you think something continuous wouldn't be advisable?
All of us are like this.
Yeah, I think that nobody is speaking here. Thank you, Erika.
Because there's probably two, like you would expect two different like sections of sloping of things, because there would be the weight loss section and then the weight maintenance section.
Exactly. Yes, as Cassia said, in this case, based on this study, we are expecting some differences between like phases or stages, not something linear or continuous. Sorry. So I read many different answers, and there was something that I wanted to ask you. I forgot it now. Sorry for that. However, if this thing is not continuous, what kind of pattern of change could we use here? How could we parameterize occasions or fixed effects here?
Do
Some-
slope and deviation slope?
Some, yes.
A piecewise model?
Yes, piecewise slopes. As Hillary also said, because there is a definite change point. Yeah, because we are interested in change, I would say, related to phases, Hillary, or different, how could I call it too? Procedures, yes, steps maybe. Yeah, but this idea of discontinuous change, to me, that's like the key phrase, discontinuous change. And if we use piecewise slopes, what do you think that will happen in this model? How many slopes should we have here?
Two.
Yes, 2 slopes. How many data points we have right now?
Not enough.
Not enough, yes. We have 3 data points, and you want to put 2 slopes in your model, and you have a fixed intercept already implicit there. What do you think will happen if you put 2 slopes in this model?
It's not a model, it's just a description, right?
That's a good answer, yes. Why? Let me show you this. Right now, if you want to put 2 fixed effects, 2 slopes to represent the change before the program, after the program, and then how people maintain weight, you will have 3 data points which is not different to fit a saturated model. So for this specific model, I think that we don't have differences between the saturated version and this piecewise model. So
We would call it a reparameterization.
yes, yes. So we are just reparameterizing our fixed effects, but I think that the saturated version or this version with two piecewise slopes, they are equivalent, right? Not likelihood equivalent, but will generate the same predictions. Yes, because the parameterization of the fixed effects can change the likelihood of the model, right? I wasn't aware of that, but that can be the case. So, yeah, I wanted to ask something, but I forgot it. That's annoying. I mentioned that, yeah, because I read a lot of different answers, so I wanted to ask you that. Well, maybe later. Questions about this answers, sorry. What could be done differently? So instead of linear change, instead of one fixed effect to describe the linear change between occasions, we could use a piecewise slope model. Because in that case, we would be capturing the differences between the phases we are interested in. Okay? Oh, yes. Now I remember my question for you. About in the individual differences, because remember that we are also interested, well, they are also interested in individual differences. How many random slopes could we have in this model right now?
Oh, we could not, right?
That's what I'm asking this. How many random slopes could be added to this model right now?
Do you mean if we do piecewise, or do you mean if
Yes,
we do
if we do piecewise, yes.
If we do piecewise, we can't, I think.
Are
I'm
you
not
sure?
No.
Okay. Why? Because we know that in terms of fixed effects, we can add n minus 1 fixed effects, where n is the number of occasions we have. So we have 3 occasions, we could add 2 fixed effects or 2 slopes. That's why when we add these 2 fixed slopes plus the intercept, the model would be saturated. Now, in terms of random slopes, we know that we could add n minus 2 random slopes. So in this case, we could add 1 random slope that would be describing the individual differences for the first fixed effect, which is the difference between before and after completing the program. But we couldn't add the other random effect for the other part, which is both in response to the training and success of weight maintenance. So when I was thinking about it, it was like, we could even answer that question fitting a piecewise model just because we have 3 occasions. Not enough data. So I wanted to ask you that because I read one or 2 answers mentioning that. So thank you for this to the students that mentioned that, because after reading those answers, I said, yeah, they are right. So thank you. Now, for question 3, the researcher also tells you that this project will provide pilot data to help inform a larger data collection effort. Do you have any suggestions on how they might change their study design to be more useful in answering their primary questions? There are 2 things that most of you mentioned.
Adding more data points.
More data points. Why? Why we would like to add more data points?
We want to fit a piecewise model, so we just need more data.
Exactly. That's the answer most of the time. The more, the better, right? So if we are interested in changes over time, we should try to get as many measures as possible, just to make sure that we are trying to, well, there are different advantages of that. One of them is precision. The other is that maybe you can try to fit different kind of change over time. Maybe the piecewise is the correct one, just because the research questions are related to this idea of phases or differences, but maybe we could try other options, as many of you mentioned. Now, I have a question here. Does the fixed intercept count as one of our n-1 fixed parameters? No, I don't think so. Yes, exactly, yes, because the fixed intercept most of the time will be there. Now, I know that sometimes we can remove the fixed intercept, but I think that that's related to other purposes. Yes, not in this context. That's possible, but not here. Well, not for the things that we are covering here. But for some models, we can remove the intercept. So we will be capturing whatever we have in the data with the fixed effects directly. Is that the answer that you were looking for, Hilary? Awesome. So yes, more label 1 data, more time points to describe the differences after and before the completion of the program and how the results were kept in time. What's the other thing that you would mention? More sample size at level 1?
More samples, more participants.
And more participants, of course, especially if we think about statistical power. I think that in these models, if you want to capture individual differences, you would try to collect as many participants as possible, just to have more statistical power. So those are the two things that I include here. Do you have more comments about this? Something that you think that could help researchers to improve this?
Some kind of control could be nice, either a different group that didn't go through the treatment or the same group but do a couple of measurements at baseline, so you get a measure of like within person fluctuation before treatment, and then after the treatment, before the follow-up, you do a couple of occasions so you get an idea of like within person fluctuation.
Yes, yes. More data to describe baseline, you mean?
That could be, I think if you didn't have a control group that didn't go through the treatment, then you
Oh,
could compare, like, each participant could be their own control group if you're looking at, like, fluctuation before and fluctuation after treatment. Because we know weight is often not very stable in people, so if we have just one baseline occasion, like, you know,
yes.
I weigh more after Thanksgiving than before Thanksgiving.
More data. That's the key. And one thing that I read too, many students mentioned the relevance of covariates for this study. That we can get information, well, additional information about subjects and maybe the context. So that could help us to get more information about their conditions. So that's all. Do you have any additional comments, thoughts, impressions? Something to say?
Another question regarding the
Yes.
covariates that you just mentioned. Did we have any models including any covariates yet? That's one thing that I was thinking about.
Yes.
We are only treating the time as
Yes.
the only variable in our model.
Yes, we have been working with time because I think that time is the most important thing so far. But I know that one of the last units include level 2 predictors, if I'm not wrong, person characteristics.
And that will enable controlling for something in the model.
Yeah, then you can control for things that would affect weight that have nothing to do with weight loss.
Oh,
Because there's probably a lot of that.
Exactly. Yes.
Height, gender,
yes.
People attributes. Yes.
That's
Yep.
great.
So that's all. Thank you for your time. Well,
Thank you.
thank you for your time. You must be here. Bye.
Yeah, please take some candy, pass it around. So, welcome back to me. Thanks for playing, everybody. So yes, lots of good ideas on how to improve this kind of design, include covariates. Some folks mentioned also that you might want to have multiple measurements of weight because it does fluctuate. So almost like a measurement burst design where you weigh yourself multiple times within like a 2-day period to get some kind of, less fluctuating type of thing. In terms of why some of that stuff matters. So if someone uses ML with a small sample and they don't use REML instead, what happens? Like, what are the consequences of that? Because you all figured that out, that you need to use REML instead, but the question is why? What do we think?
Doesn't it make you think that you have more confidence in your answer than you really do?
Yes. Right idea. Put some more words in there.
If you use ML, it might decrease or underestimate the standard error for each parameter.
Yes, but the reason that the standard errors are underestimated is upstream more. It's the level 2 variances that are too small.
Because in ML we include the fixed effects.
In ML, you are treating the fixed effects as known rather than unknown. So the version of the variance is like divide by n rather than n minus k. So as a consequence, the random effect variances are underestimated in ML in smaller samples. And so if you have too little variance, you have too little standard errors, that means you have too optimistic p-values for the corresponding fixed effects. So that's why. And how much people is enough? 100-ish, I don't know after that. It depends on how many fixed effects you have, because it's n minus k. So what else I was going to say in terms of weight loss here, Paint 3D won't be available anymore. What? They're going to take Paint away?
Paint 3D.
Yeah, this is fancy Paint.
Just don't update your
Yeah. So their design would be something like, okay, here's my weight at baseline. Hopefully I'm able to lose weight if that was my goal. And then after the study treatment session is over, then I keep the weight loss off, right? So that's what they're envisioning. Do you think that's how it works in the real world? Nope. Nope. So if you only have these 2 data points and then the third one at the end, this is how you would have to believe that it works, because you have no other alternative. But in reality, it's probably more like, oh, I'm going to lose it, and then I get tired of this, and then I maybe lose a little more, and then I plateau. And so there's going to be like sorts of undulations and things. So you would probably want to put more data points at the beginning when people are more likely to be initially losing weight or water weight, as it probably would be, and maybe fewer towards the end. It just depends on the type of change pattern. So in terms of piecewise models, I would say probably the 2-slope version would be most useful for this, because you're expecting them to change here. So the question is, did the program work? Did they lose weight? But then you're expecting them not to change. Like what maintenance would be keeping constant the loss that you have. So if there is a slope at all during the second phase, that's an indication that they're regaining weight, and that's not good. Or alternatively, they could keep losing weight if they're continuing with the behaviors that they wanted to do. So a lot of possibilities, but more data is for sure a good thing. And a control group, or a control period if you can't get another group. So, question?
I have a question regarding the scenario. If you are measuring another outcome added to the weight, for example, the glucose level or cholesterol
Sure,
or something
cholesterol,
like that.
something like that.
Is that something called like multivariate, multi-level modeling?
Yes, it is.
Okay. So when can we separate that into 2 separate models estimating each outcome, and when are we merging both outcomes and put them on the same model?
Great question. So if we had more than one weight loss outcome, which I'm guessing most of these studies would. By the way, this story is based on a real study that I helped analyze the data for. They had percent body fat. I think they had waist size, probably some biological measures like cholesterol, A1C, that kind of stuff. Yes, if you wanted to say, did people who lost more weight than other people also improve their cholesterol more than other people? Like, do these things travel together, so to speak? You would need a multivariate model to do that. And essentially what it would be is like a giant G matrix that has the intercept variance and the slope variances for one outcome and for the other outcomes. And so then all the covariances tell you whether the slopes are related to each other or whether the intercepts are related to each other. So for instance, people who have more weight to lose probably have a stronger trajectory in terms of weight loss because they have more room, for instance. So the intercepts and slopes will be related, but you can look across variables like that too.
And this is available for all packages?
So the best way to do it, I would say, that gives you the most flexibility is multi-level structural equation modeling, or regular flavor structural equation modeling if you have balanced data. You can technically trick Elmer and SAS mixed and Stata mixed into doing these things, but then the relationships among your random effects can only be undirected covariances. They can't be directed. So you can't have slopes. Like you can't have the change slope predicting the change slope in a directed path model kind of way. And that means you wouldn't be able to have moderators of that relationship either, or mediators of that relationship, as it were. So yes, would you like to learn how to do multivariate, multi-level modeling?
Yes, I
Are you going to come back in the spring and learn it then?
am. Yeah, maybe sooner.
Maybe sooner? Well, the materials from last time are still up.
Okay.
I've written a lot of things on this topic, so chapter 9 in the book covers these models. Other stuff that's on reading lists of various classes too, I can send you. If you can send me an email to remind me that we had this conversation, I
Yeah.
can send you some more. Or you can wait until January and see the syllabus, you know, whichever. But yeah, you can do all that stuff. Before you run, though, you got to walk, and before you walk, you got to crawl, and that's what we're doing. We're crawling towards the end of the semester here. And we are going to get to predictors, I promise. Just not time-varying predictors, because it turns out you really need a model for those most of the time. Okay, so no more story time. I don't need to save my work. Thank you. Are we ready to do some reviewing? Would that be helpful? So I have lecture 7A as a step-by-step, because folks like to have a guide or a plan in place. And this is also written about at the end of chapter 6. I have like an appendix that goes through the same sorts of ideas. So let's just cruise through this here, one step by step. So for all time-varying variables, we start at the same place, and then based on what trends you see, then you kind of diverge into choices for what you're building in a model. So what the terminology that I'm using here, unconditional, is a term that people mean that they have only time in the model but no other predictors. So you start with empty, which has nothing, and then you work your way up to unconditional time, which would have whatever fixed and random slopes or patterns of correlation that you need to address correlation of occasions from the same person. Then that logically sets the stage for what your predictors have to do. So we're talking about the process of building through this unconditional stage as a new reference point. So step 1, empty means random intercept model, otherwise known as unconditional means or just empty. And I write it this way to try to be clear that we have a fixed intercept and a random intercept, and the residual variance is always there whether you ask for it or not. So this is the worst model that we can have for longitudinal data. It is going to have the highest -2 log likelihood or the lowest if it's the worst model. Which way does it go? We got hand gestures from the Zoomers. No disco in this class. That was the other class. So -2 log likelihood. Is smaller better or is bigger better?
I think smaller.
Smaller's better. So this model should have the highest of the ones we would entertain. Its purpose is to tell you how much of your data is actually cross-sectional. So we calculate an intra-class correlation, which divides the variability into how much is level 2 between people and level 1 within people. And that number gives you the proportion of variance that is between at level 2. That is due to person mean differences. Said differently, it is an effect size for the amount of person dependency due to mean differences. That's what an intra-class correlation will tell you. In most cases, this will not be an accurate representation of the variance structure, though, because it assumes people differ from each other in only one way. But it is a starting point, at least. And the other thing that's useful about this is that it gives you a sense as to which kinds of predictors are going to be most useful. So if most of the variability is between persons, what kind of intra-class correlation would that be? Give me a number that would be consistent with that. If most of the variability in your outcome is between.
Like 80-something% is between persons.
Say that louder, please.
Like 0.82.
0.82?
Be high between person variability.
Yeah, what do you think?
I think
0.82
above
is
80.
above 80?
Yeah.
Yeah, high numbers. So ranges from 0 to 1, past 0.5 would be more between than within. So if you found an interclass correlation of 0.8, that means that most of the variability is due to individual differences in the intercept. So you would need individual differences kinds of predictors, things that are constant to a person. That would explain why some people have higher means than other people. If, on the other hand, your ICC was something like 0.2, then person mean differences are relatively less important and time differences are more important. Then you would need predictors that change over time, because then it's like, why are you off your line today? What was going on today that didn't happen yesterday? The tricky part about within person predictors, though, is that they're never truly just within. So if I ask each of you, like for every day for a week, how stressed out you feel today, some days are going to be worse than others, right? But do you think there's also constant person differences? Some people are going to report more stress than other people no matter what day you ask them? Yeah. So in that sense, what we think of as time varying stress is actually person stress too. And for the same reasons why we would need a multi-level model in the first place for our outcome, we would need to pay attention to the sources of variability in our time varying predictors. And for those of you who took the clustered multi-level class, you're like, oh, is she talking about smushed effects and stuff? Yes, I am. But it gets even harder in longitudinal because there's multiple ways in which you can smush an effect. Stay tuned for the spring. That's all I'll say about it for right now, though. Okay, questions on this much? All right, then. Step 2, we have not spent much time on in this class. This is coming in the spring as well. Deciding on a metric of time. It doesn't necessarily end up as straightforward as you might think. So what I tend to do most of the time, my preferred default is to use time and study. So like the first time I see you is time 0, and then my time variable keeps track of how long it's been since then in exact time. The reason I like that is that it can't be wrong. It's tracking the purely longitudinal component relative to whenever you got there as time 0, how much farther in time is it? Other options, though, would be something like chronological age or time to event. The trick with these, though, is that if people differ in these time metrics at the beginning, that is a source of individual differences. So then you have cross-sectional variation in how old they were to start with. You have longitudinal variation in how old they're getting during the study, and those are two different things. So age differences versus age changes. And the same thing happens in terms of other processes. So for instance, time since diagnosis is one that's used a lot in medical settings. If you have something like a divorce or a chronic event that is very impactful, time since that happened would be a way to look at that. That latter thing, though, only would include the people who have that time, have an event. Otherwise, you wouldn't have anything structured around. Whereas everyone can participate if it's time and study. So this is chapter 10 of the book. It's a more advanced topic, but I just want to put a pin in it saying that this is something that you do need to think about in practice in a lot of settings. So does anyone have data that they're working with that this sounds like? Accelerated longitudinal designs, as they're called? No? Okay, well, they're common in some areas. Yes. Okay, someone said yes. Do you want to tell us about it or type about it? Don't have a speaker. Okay, well, thank you for saying yes. There's nothing worse than constantly lobbing softballs and everyone's just like, nope, I'm not going to play. So, another one, we collect 6 months to 18 years ongoing. Yes. Yeah, so that's a fairly wide time frame. If you just put age in and call it good, then you would be ignoring potential differences in when someone was that age. So think about, the effect of COVID, for instance. My son is 9. Is somebody who turned 9, 10 years ago going to be following the same trajectory as my 9-year-old? Probably not. In educational settings, schools are constantly trying to improve outcomes by changing what they're doing. They introduce new programs or professional development opportunities. And so, is this year's batch of 4th graders going to be the same as next year's batch of 4th graders if they change processes within the school? Maybe not. So those are things to think about. It's like, not just how old you are right now, but your age in this current context. So I used to tell a story when I would give talks about this about my grandmother. We called her Mimi. And at the time I was telling these stories, I was about 35. And I would tell people, if age is the only thing that matters, then I could look at Mimi and be like, that's what 85 is going to look like for me. Despite the fact that by the time Mimi was my age, she had had 7 children. She had never had a job outside the home. And up until fairly recently, never wore pants. She only wore skirts, because that's what ladies do. So other than that, that's what 85 will look like for me. No, there's a context there. So being 35 in whatever year she was 35 is very different than being 35 when I was 35. And when you're all going to be 35, it will be different still. So anywho, this is the whole thing, point of the story. Decide on a centering point. So in some of your answers, you mentioned the occasion coding as being problematic because of the 1, 2, 3, and 0 is not within that range. I agree that that's a problem, but it doesn't necessarily make the model incorrect. It just means your intercept refers to a point in time that was impossible to observe. The one situation in which you would want to be extra careful about that is if you're so far away from where 0 actually is in your metric of time, that can cause estimation problems for the random intercept. So once you add a random time slope, then the random intercept variance becomes conditional on wherever time 0 is. So if you have older adults and you forget to center time, then your intercept refers to a newborn, as indicated by people who are 80 and above. That's not going to work very well. So that's where it can transition from just not weird but to wrong if it breaks the model. Yes?
Can you just repeat that again?
Yes.
Thank you.
Okay. So let me back up and explain a little bit more where this is coming from. The fixed intercept is always the expected outcome value when the predictors that have fixed slopes are 0, right? Same thing, but I'm going to put the word random in front of it. The random intercept is always conditional on the predictors that have random slopes being 0. So if I have a random slope for time, my random intercept is specific to time 0. If I have a random slope for time varying stress, my intercept is also conditional on time varying stress being 0. It's the same exact logic. And so if 0 is too far away from your data, that can cause estimation problems. Then it would be broken. But otherwise, it's just weird and not necessarily wrong. What you'd want to ask yourself is, where do I want a snapshot of individual differences? It's not necessarily at the beginning. So if I'm concerned about the effect of some kind of intervention or treatment, I want to know about how they ended up, right? What are the differences in the ending point of this process and what predicts who ended up higher than other people? The beginning is not necessarily the point of most interest. It's really context specific. In chapter 9 of my book, I have an example where I centered time at the end because I was supposed to be looking at problematic, risky behavior in adolescent girls from like 12 to 18. Well, there's not a lot of problematic behavior in terms of like smoking, drinking, shoplifting, all that kind of stuff at 12. There's probably more of that at 18. So like, and especially given that you can be tried as an adult at 18 and, you know, prison sentences and things are going to be different in most places, that's a bigger impact. So in that case, putting it at the end probably makes more sense. There's more variability there, and the variability matters more in terms of how it translates. But time 0 is up to you, wherever you put it. You can also use estimate statements to get predictions at other times. So I've been trying to set us up for this idea in terms of like, what would the linear slope be at time 4? What would it be at time 5? You don't have to recenter time to find that out. That's a linear combination. However, if you want to get the variances at those other times, then you're probably best off just re-estimating the model after recentering time to where that 0 point is. So this is a choice of specification or parameterization, not necessarily like estimation. Like this is a choice that you can make. Then we try to figure out, what are we modeling? So if you have balanced time, what does that mean again? What does that idea mean? We talked about this last week.
Same schedule.
Same schedule, yes. Not necessarily equal interval, not necessarily complete, but same schedule. So if you have same schedule of timing, then you can estimate a saturated means model and make a picture and see what the shape is. So is it straight or is it bendy? Is it continuous or does it look like there's a breaking point, a discontinuity? That should guide you towards a family of models of change that would look appropriate and make sense theoretically. If time is not balanced, so people came in, on time 1.2 and 1.7 and 6.9 or whatever it was, then you can conveniently round into nearest intervals just to make a picture, but I would not report the fit of that model. I would not judge anything with it. It's just literally for descriptive purposes. And then you can see what type of analysis you would want to use with exact time. And I have a note here. This is a question I get actually really commonly. In method sections, it's very common to report means and standard deviations for each of your occasions. The problem comes in is that if those are generated just using descriptive statistics, they have an assumption of missing completely at random, meaning there's no reason why people who didn't come back didn't come back. That's probably not true. The means that are being estimated in the model, so the estimated means, the saturated means, those are estimated under an assumption of missing at random, which means random after conditioning on the data you do have. So those may diverge quite a bit if you have a lot of missing data and to the extent that it's missing for reasons. So I think if you're going to report descriptive statistics, you need to be very clear that that is a different result than whatever you're plotting in terms of trajectories and whatever you're modeling. The trajectories are trying to capture the saturated means, not the observed data means. And if you're like, what do these acronyms mean? There's a class on that next semester. Brand new class Jonathan is offering on missing data using Craig Ender's book, new book, so I would highly recommend that. You may see me in it, to be honest, because he's going to Bayes it up, and that's like one of the holes in my knowledge. I don't know that as much about Bayes as I probably should. But in my defense, I teach 6 different classes, and I can't know everything. I'm going to run out of room at some point. There was an episode of The Simpsons about that. I don't know if you remember this, long time ago. Homer started learning French, and he started forgetting English words, so he didn't know fork anymore in one episode. So that's what will happen to me. If I start learning sand, then like sass and stata will like leave my brain. But anywho, not it, but you can generate that. And then next, what do I do? What if I have no change? So your trajectory may be flat. That's fine. So I have kind of a continuum here of types of designs and models that they would lend themselves. So if I start with the right-hand side, like the end of pure within-person change, this would be like your classic growth curve. Observations are far apart in time so that you have room to see people change. Measuring change and predicting individual differences is the whole point of the study. If that is the case and you have obvious change in your trajectories, then some kind of fixed slopes for change over time. And that's where like linear and quadratic is sort of one family, piecewise is another family, exponential stuff, there's a whole bunch of nonlinear models, there's reparameterizations of things, there's logistic curves, there's all kinds of choices here. But choices related to change over time is the idea. And then that would naturally lend themselves to random slopes for time as well. So each of these can have individual differences in the extent to which people show it. If you have a lot of occasions, you might also worry about correlation in the R matrix that's left over, if you've mentioned that in here. For only 3 occasions, though, you wouldn't need to worry about that. I'm pretty sure there's an equivalency class between an AR1 model in the R matrix with a random slope model for linear time. I've stumbled across that being like the same thing before. So with 3 occasions, you can't really do much of that. So this side is fairly clear. The left side is the other end of the spectrum where time is irrelevant. You're just trying to get a lot of data from people to see how things fluctuate within persons. So if you're measuring something like, stress or well-being or social support, things that don't change or you're not changing them, you're not trying to intervene, then you may not need anything related to time. But you do still need to worry about correlation patterns. And so this would be where like the AR1s and the topalitzes and all that kind of stuff might come in. Unstructured, if you have very few occasions, would be fine. And then the middle is the tricky part. time is not supposed to be relevant, but it is. And I have some examples of when that, a couple examples of that. I can tell you one. There was a study that I helped analyze data from at Penn State where they called people every night for a week and they asked them questions. And one of the questions was like, did anything stressful happen today? And if they said yes, then they got like a follow-up set of 10 more questions about what happened. Well, by the end of the week, people were like, nope, nothing happened, okay, bye. And there was this magical decline in stress throughout the study. It was amazing. No, people got smart and didn't want to be on the phone with you. So, older study, obviously. Now they would just like buzz you on your phone, and then you'd be like, no, nothing happened today. So in that case, the student had to model, like it was like a quadratic change model of stress across days. It was artifactual because of the way the data were collected. They weren't expecting it, but you can't ignore it. So in that case, you might have some kind of a hybrid model where you have fixed effects that cover average change patterns, but there may not be any individual differences in that if it's not a real process. So maybe alternative covariance structures with fixed slopes for time. You can mix and match things together. They don't have to be the same on both sides. Okay. What do we think about that? Yeah, want to see a couple examples from previous student projects? So this was another Penn State student. This is a number of drinks you intend to have, alcoholic drinks, and these are college students who probably can't drink legally, but that's not going to stop them. So these are the individual trajectories, and the saturated means looked something like this. So this student was fitting like cubic models and quadratic models because there's this, this peak or whatever. Nope, there's a simpler explanation. It turns out that they had 3 cohorts of students that enrolled through this thing, and once you align by when spring break was, the story changes quite considerably. Like, she had made up this whole theoretical explanation related to like cumulative effects of stress during the semester, and that's why it goes up slowly and then it comes back down as you get no, spring break. And you can see it, like the axes aren't aligned because I had to make this after the fact, but you can totally see at time 0, which is spring break week, there is a good deal of individual differences. So if you were fitting this model, what would you put here? What would be a good way to represent this spring break phenomenon?
You mean with centering?
Say it again?
You mean with centering?
Well, I've centered it so that 0 is like this point right here.
Sure.
Yeah, what kind of slopes do we need for this? Anything?
Negative quadratic.
Could be a quadratic, although this is kind of pointy for a quadratic. Piecewise, could be an option before and after. There's a definite change point. It doesn't look like there's much change on average before or after, but there's just change here. So I think what she ended up with was one dummy code. Is it spring break or not?
That makes sense. Yeah.
It fits.
Yeah.
So that was a fixed effect. The fixed effect would say, on average, students plan to drink, 8 more drinks this week when it's spring break than they do when it's not spring break. Could that dummy code have a random effect to go with it? If I have a fixed effect of time, where time is whether or not it's spring break, can I have a random effect to go with it? Sure. What would it mean?
Some students don't drink that much at spring break.
Yeah, individual differences and just how crazy they plan to go. Because you can see, some people are like 50. Yeah, if I have 7 beers a night for 7 days, I could hit 50. Hashtag goals. And then other people like, this is me. I couldn't afford alcohol in college, and I spent my spring break working extra shifts to make extra money while everyone else was gone. So, yay. How many drinks? Yeah. So her study changed quite a bit because it was intended to be like, fluctuating things that relate to drinking, but then this signal beyond that was what predicts how crazy some people are going to go. They intend to go. So this is an example of when you didn't expect to have change, but you found it anyway. So we had to pivot. Here's another one. This is the end result of the measurement burst study that we are analyzed in chapter 6. So it is 6 occasions within a 2-week period, repeated at 6-month intervals. So there are 2 time trends visible in these data that were not intended to be there. This is negative affect is the outcome. So within each of these bursts, or actually, let's do the other one first. The overall trend here is this line is going up. As people are getting older, they're getting grumpier. There's a 0.24 increase per 6 months. So note the unit thing, right? This is, the interval here is a 6-month interval. That's what 1 means as a unit change. But then within these bursts, you see some kind of reactivity to measurement. Within a burst, negative affect is going down. And what the hypothesis was is that this study data, these were collected in a nursing home. These are people who are lonely. And, the testers come in, and by the end of this, the 6 visits, like, they're greeted with cookies and tea and their friends, and, like, it's kind of like a little intervention. The act of having people being paid attention to made them less grumpy, but it didn't last. So negative affect is a classic example of something that you would think just fluctuates and it doesn't really change, but this is change. Yes, if you have people in nursing homes, go call them. They're probably bored. My mom's doing her part with her singing group, trying to keep them entertained. So we can all do our parts. Actually, one more story about the same study. They measured vocabulary, and they would tell each other in the dining hall, like, what was on the test that day. So the people who were tested later actually did better on the vocabulary measures than the people who were earlier. Yeah, the older adults were behaving a lot like undergraduates, I think, in these situations here. But, okay. So let's say that you have some kind of change. Whether you intended to have it or you got stuck with it, you have some sort of change pattern. Then your question would be, on the mean side, what kind of fixed effects do I need to describe the average trajectory? And these are the choices. So there's lots and lots of choices out there. I tried to give you an introduction to some of the most common ones, and you can learn about others. The nice part about this in terms of deciding what is needed is that you can test fixed effects directly, look at the p-value, see what's there. Things that are hierarchical, you want to make sure that you keep that in mind. So if you have a polynomial model, if you have a quadratic slope, the linear slope needs to stay with it for the quadratic to have the right interpretation. Other things like piecewise models are not hierarchical. You could have both in at the same time, or three slopes even. On the model for the variance side, the focus would primarily be on G. What random effect variances and covariances do you need? Which aspects of change show individual differences? That in turn introduces heterogeneity of variance across time, as well as heterogeneity of correlation and covariance across time. And we would also want to check in the R matrix to see if there's any remaining residual relationships there. And for this, we would do likelihood ratio tests. So difference in -2 log likelihood, preferably using REML for all of this, but ML is okay if you have a big enough sample size. So then we would end up with something like this. So let's say that we only need one type of slope. I would have 3 different piles of variance in my model. I would have individual differences in the intercept at level 2. Why are some people higher at time 0? I don't know. We need person information to go predict that. Why do some people change more than other people? That's at level 2, and we need people information to predict that. At level 1 is E, which is why are you off your line today? People things cannot directly predict that. Only time things can. And every time we add a fixed effect, it should be targeting one or more of these piles. And that would be where we can use a pseudo R-square to see how much of the variability was reduced for each of these things. Anytime that you add a random effect, though, you are not explaining variance. You are making a new pile. So random slopes to me do not explain variance because they're still sources of error. Why is it that some people change more than others? Why is it that some people are more susceptible to stress than others? We don't know. But we're going to find out. We get to start adding predictors. He's like, yes, finally. I know. Now, what if you don't have change? That's okay. If you don't, if there's no change in your data on average, you may not need any effects related to time. In that case, I would focus on the patterns that you see in your unstructured matrix. I like the idea of starting with the random intercept and then seeing what's left, because that's usually a simpler structure than trying to put everything in R. However, if you only have a few occasions, like 2, 3, 4, unstructured is probably fine for that, if you just want to go with the easiest route. You can compare alternative models if you have the same fixed effects. So REML is, the REML likelihoods are on different scales. If you have different fixed effects, they're not comparable. So we got to keep that part the same. We can do likelihood ratio tests and look at AIC and BIC for that as well. So on this side then, you might be in one of these two situations. If you have a random intercept, then you would have 2 potential piles of variance. But if you don't, like if you just have an R matrix, then it's all shoved together. There's nothing wrong with that if it fits. What you lose, though, is the capacity to say, I got this much of the level 2 variance and this much of the level 1 variance, because the model's not set up that way. But you could say, I got this much of the occasion 1 variance, this much of the occasion 2 variance, and this much of the occasion 3 variance. You could do something like that instead. So why did we spend like 12 weeks on time? I have a reason. Here's the logic. So we start with fixed effects of time, because that's what the random effects are varying around. The fixed effect is the middle. Random effect is how far off you are. So we can't have random effects unless we have fixed effects. Those random effects have variance. We have variances across people in intercepts, linear slopes, quadratic slopes, what have you. Those are the sources of individual differences that the person level predictors are going to be trying to account for. So the effects of those predictors then have to be specified as a function of the time effects we have. So for instance, if I have a linear only model, then I only have 2 kinds of individual differences. There's only 2 things that the predictors can do. If I have a quadratic model instead, where I have a random quadratic, then there's 3 things the predictors can do, and so on. So the model for time logically constrains what the job is of the person level information. And after we build different trajectories for different kinds of people, we can look at time-varying predictors, and their job is to soak up whatever's left over. Why are you off your line today? Well, you got to get the line first before you can see why you're off it. So the fixed effects of time and the random effects of time logically dictate what the rest of your predictors have to do. That's why we spent 12 weeks on time. And that's why the clustered class gets to have a lot more different kinds of data examples, because I don't have to spend 12 weeks on time in that class. Because people are exchangeable. So this whole thing is just not relevant in that domain. So here's some example sequences of going through steps. There's other ways to do it, and I'll show you, I think, a couple other ways in other examples. So that's for polynomials. This would be for piecewise models, and that's it. So where we're headed next then, on Thursday, is predictors. Hooray! You're like, oh my God, finally, something I can do. But no, they have to go through this part first. The good news is that adding predictors is not different than any other linear model. Like, you put them in, they change your predicted intercept. You talk about them like 1 unit change in this predictor is this much change in your outcome. The bad news is that pretty much everything is going to turn into an interaction term. So if I put in, say, a main effect of a treatment group, whether you're in a control group or treatment group, that is adjusting the intercept. If I want to ask the question, did the treatment group grow more over time? What kind of fixed effect answers that question?
Interaction between group and time.
An interaction between group and time. Did this group grow more? What if growth is a quadratic? Did the treatment group accelerate more? How do I answer that question?
Interaction between group and group squared.
Group and group and time squared. A 3-way interaction. Yes. So this is why chapter 2 of the book is all about interactions, because if you don't have that, like, you're dead in the water for all of this. So, but if anyone's like, oh my God, I don't remember interactions, or it's been too long, in 15 minutes, I'm going to be talking about interactions. So You can hang out with the other class, or you can watch it on YouTube, or you can review chapter 2. But if you're feeling shaky on those, I would recommend revisiting that material prior to us going through the next example. That will be your last homework, will be predictors in these models. Okay, questions or comments? Yes?
We've been talking about the right side of the model, so we didn't talk about the y values at all. So are we expecting like special type of the outcome, or what we are measuring?
You mean what kind of outcomes?
Yeah, are we expecting that to be usually continuous variables? Or?
In this class, yes. The models are for conditionally normal residuals at level 1. But there are generalized versions of multi-level models, and all the same, basically all of this stuff readily translates to that, and you add link functions, and you add different distributions in at level 1 for what the conditional distribution is. I have a couple examples from the clustered class. I think I have a binary one, an ordinal one, and maybe a count one I did in that. But I don't have room to put that in here. I did not get to that in advanced longitudinal last time. I wanted to, but I didn't get there. So, yes. There is a really good book that just got a second edition, actually. So, Linguo, you told me that the link was broken, I think, the other day. I fixed it, and in fixing it, I noticed there's a second edition of the book. So, Walt Stroop has a book called Generalized Mixed Effects Models, I think, something like that. It's linked from one of the last slides of lecture 6. And apparently, how it got revised is he had 2 of the students who were in the class the first time he taught the book help him revise the book to make it easier to read. And I was like, oh, thank God. It's a difficult book, I'm not going to lie. But it's a really thorough one, so I would recommend that one. There's also an older one. Hedeker and Gibbons have a 2006 longitudinal book that covers generalized extensions as well. So. All right, other questions? Then I hope to see you Thursday. Thanks for being here. Grab some candy on the way out, even if it's just licorice. Yeah. No, I understand. Thank you. Bye for now.